two projects. In this video, we are going to explain the project Skin Cancer Image Classification using CNN's a comparative analysis. Before diving into the execution, let me give you an overview of the project. So, skin cancer arises when ultraviolet, that is UV radiation, penetrates the skin, causing mutations in the DNA of skin cells. So, these mutations disrupt the normal cell cycle, leading to uncontrolled growth and tumor formation. Early detection of skin cancer is very important because it allows for prompt intervention and successful treatment, greatly improving patient outcomes. Traditional methods of diagnosing skin cancer rely on visual inspection by dermatologists, but this approach has limitations. Human error, variability in interpretation, and the subjective nature of visual assessments, that is, opinions might change because of change in lighting, background, etc. So, these limitations can sometimes result in misdiagnosis or delayed diagnosis, impacting patient prognosis. So, there comes deep learning. Deep learning techniques, specifically convolutional neural networks, that is CNNs, offer a promising solution to these challenges. CNNs are a type of artificial neural network inspired by the visual cortex of the human brain. They excel at processing and analyzing visual data, making them well suited for tasks like image classification. In the context of skin cancer diagnosis, CNNs can be trained on large datasets of annotated skin lesion images to automatically recognize patterns indicative of malignant or benign lesions. By learning from a diverse range of examples, CNNs can generalize their knowledge and make accurate predictions on unseen data. So, during the training process, they learn to identify common features associated with malignant lesions, such as irregular borders, uneven color distribution, and asymmetrical shapes. Once trained, they can analyze new unseen images and provide a prediction regarding the likelihood of malignancy. So, this automated approach to skin cancer diagnosis offers several advantages. It reduces the reliance on subjective human judgment, leading to more consistent and reliable results. Additionally, CNNs can process large volumes of data quickly, potentially speeding up the diagnostic process and reducing the time to treatment for patients. So, we will be using deep learning techniques, deep learning models for skin lesion classification in this project. Now, we'll look at the workflow. So, the International Skin Imaging Collaboration, that is ISIC dataset, is used in this project. It provides a large collection of skin lesion images annotated with labels indicating whether they are benign or malignant. So these images form the basis for training and evaluating CNN models for skin cancer classification. To make the dataset suitable for deep learning models, the dataset undergoes a process called image processing. One crucial aspect of image processing is data augmentation, which involves creating additional training samples by applying various transformations to the original images. This step is very important because it enhances the quality and diversity of the data set, making it more robust and capable of handling different scenarios. One tool used for data augmentation is Image Data Generator. It offers a range of transformations including rescaling, shear transformation, zooming, horizontal flipping, and reshaping. So, rescaling ensures that all images have consistent pixel values. Shear transformation introduces slight distortions to simulate real world variations in perspective. Zooming adjusts the scale of the images, mimicking different viewing distances. Horizontal flipping creates mirror images, increasing dataset diversity. And reshaping ensures that all images have the same dimensions. So, in this way, we will train the original images from different angles so that the models can generalize well. After image processing, we will split the dataset into two sets, train and validation sets. Train set is for training the models and validation set is for evaluating the model's performance. So various CNN architectures are developed and analyzed for their efficacy in classifying skin cancer. So these architectures include GCN, VGG16, ResNet 50, MobileNet, EfficientNet, Exception, and a hybrid model which combines Exception and EfficientNet with GCN. So we will be training all these models and will evaluate their performance using different performance metrics like accuracy, precision, recall, and F1 score. And we will select the best performing one among them for skin cancer classification. So this is what happens in this project. Overall, this project focuses on enhancing skin cancer diagnosis and treatment using CNNs. So, early detection of skin cancer is very important for better outcomes and reduced healthcare costs. So, by training and evaluating CNN models on datasets like ISIC, researchers compare architectures for effectiveness. This comparative analysis aids in informed model selection. Demonstrating CNN's potential in improving diagnosis, efficiency, and accuracy contributes to advancing medical technology and benefits patients, healthcare providers, and researchers. Now we'll see the software and hardware requirements to execute this project. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language required is Python, front-end framework required is Flask, back-end framework needed is Jupyter Notebook, database needed is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we look at the algorithms built. So in the base paper, author has proposed a hybrid model combining exception and efficient net with GCN. He has compared this proposed model with GCN, VGC16, ResNet 50, MobileNet, EfficientNet, and concluded that hybrid model has outperformed all other models. In this project, for improved performance, we are proposing exception model. We will be building all these models, the models proposed by the author and the model which we are proposing, and will compare the performance of all these models using performance metrics like accuracy, precision, recall, and F1 score, and will select the best performing one among them for skin cancer classification. Now we will understand about the algorithm which we have proposed, that is exception. So exception is a deep learning technique. It is known for being good at understanding images. It does this by breaking down the process of looking at images into two main steps. First, it looks at different parts of the images separately. This is called depth-wise convolution. Then it combines these parts to understand how they relate to each other. This is called point-wise convolution. So this helps exception to understand images better and pick up on important details. One of its strengths is that it is really efficient at doing this, which is important when you are dealing with lots of images. Plus, it is great at figuring out what features in the images are important for making classifications. Another important thing about exception is that it can learn from other datasets before being used for a specific task. This is called transfer learning. So this makes it super adaptable and useful for classifying skin lesion images. So this is about the exception model. So after comparing all these models, we have observed that exception model, the proposed model, has outperformed all other models in all the performance metrics. So we have deployed exception into Flask web application. So we will be executing the project using Flask web application. Before execution, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. So this is skin dataset folder in which I have required ISIC skin lesions dataset. So we can say I have two subfolders here, train set and test set folders. So train set is used for training the models and test set is used for evaluating the model's performance. So in train set, I have two subfolders again, benign and malignant. So these are the two classes in the data set. In malignant folder, I have respective images. So these are the skin lesion images related to malignant. Similarly, in benign folder, I have these skin lesion images related to benign. So on these images from these two folders, we will train the deep learning models. Similarly, I have benign and malignant images in test folder also. On these images, we will evaluate the model's performance, the trained model's performance. So this is about the dataset, and this is sample folder in which I have benign and malignant images again. So on these images, we will test the system. That is, we will make the classifications. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes coded in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information. So these files will be loaded into the project code during runtime to utilize the train models. This is Notebook Jupyter source file, which contains a combination of code, graphs, and outputs all in one place. So Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. It stores information like sign up details of the users. So this is about the code folder. Now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I usually prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. Here we can see a sign up link, click on it. So if we are new users, we have to register ourselves first, fill in all these details and click on register button to sign up. And if we already have account, we can directly log in by clicking on this link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on login button. So it has redirected us to the classifications page. Now we have to upload any skin lesion image here and the application will classify the skin lesion as either benign or malignant. Click on choose file button. So from sample images folder, first we'll upload any malignant image. So these are the test cases I have for malignancy. I'm uploading this one. Click on open. The image has been loaded. Now click on upload button. This is the uploaded skin lesion image and here we can see the classification, that is the patient is diagnosed with cancerous tumor that is malignant, meaning it can grow and spread to other parts of the body. It is very dangerous. So early diagnosis is very important. So the application has correctly classified this skin lesion as malignant. We'll try giving another image. Click on try again button. Click on choose file. This time we'll try with this image. Select the image, click on open. The image has been loaded. Now click on upload button. This is the uploaded skin lesion image. And here we can see the correct classification, that is malignant again. So we can see the patient is diagnosed with cancerous tumor that is malignant, meaning it can grow and spread to other parts of the body. We'll try with benign image this time. Click on choose file. So I'm selecting this image. Click on open. The image has been loaded. Now click on upload button. This is the uploaded skin lesion image. And here we can see the classification, that is the patient is diagnosed with benign tumor. That means the tumor can grow, but it will not spread to the body, other parts of the body. So the tumor has been detected, but it will not spread to the body. It is not that dangerous. We'll try again. Click on choose file. This time we'll try with this image. This is the uploaded image, and here we can see the patient is diagnosed with benign tumor, means the tumor can grow but will not spread. We can see the correct classification, that is benign tumor. Similarly, we can upload any image from the test cases and can get the classifications if the tumor, the skin lesion, is benign or malignant. This is the uploaded skin lesion image, and here we can see the patient is diagnosed with benign tumor. It will not spread to other parts of the body. We can see the classification here, the benign tumor. Again, we'll try with one more image. We'll upload it from malignant. This is the uploaded image, and here we can see the patient is diagnosed with cancerous tumor that is malignant. It can spread to other parts of the body. So in this way, we have to upload skin lesion image, and the application will give us the classifications. Now we look at the graphs plotted. Click on graphs link here. Here we can view all the visualizations made. So this is the loss in accuracy curve graph of exception. In this graph on x-axis, I have epochs. And on y-axis, for this graph, I have loss. And for this graph, I have accuracy on the y-axis. So we can see for every increasing epoch, loss is decreasing. And for every increasing epoch, accuracy is increasing. That means exception model is doing well. This is loss and accuracy curve of the hybrid model, which was proposed by the author in the base paper. This is accuracy scores comparison graph, a horizontal bar graph. So accuracy is a measure of how well a model correctly predicts outcomes. It represents the proportion of correctly classified instances among all instances evaluated. This is precision scores comparison graph. Precision is a measure of the correctness of positive predictions made by a classifier. Similarly, this is recall scores comparison graph. Recall is a measure of the classifier's ability to correctly identify all relevant instances from a dataset. And this is F1 scores comparison graph. F1 score combines precision and recall into a single value. It provides a balance between precision and recall, taking into account both false positives and false negatives. So from all these graphs, we can see that exception model has outperformed all other models in all the performance metrics. Now click on sign out. So the project demonstrates the efficacy of CNNs in improving skin cancer diagnosis. It concludes that exception outperformed other architectures in skin cancer diagnosis. So, this finding highlights its potential for enhancing early detection and improving outcomes for patients, healthcare providers, and researchers in the field. By evaluating various architectures and datasets, it contributes to enhancing early detection, benefiting patients, healthcare providers, and researchers alike.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.